let's continue on and get a transfer matrix for a different situation, namely for refraction at a spherical interface. It's a little more complicated, but not too difficult. So there it looks like our usual setup for a spherical interface. I've got two dissimilar media, N1 and N2. I have a center for the spherical interface. Here I'm obviously doing a convex interface between the two media. One goes out along a radius, and that's going to be perpendicular to the interface. I have a ray coming in, hits up here at some point, and then gets bent or refracted by Snell's law. The incident ray is coming in at theta 1 with its angle that it makes with the optical axis, and it comes in and strikes the interface at a height y1. It then gets bent, and so the emergent ray, after it gets bent, after it gets refracted, it's coming out at an angle theta 2 with respect to the optical axis, and at a height y2, and pretty obviously y2 and y1 are equal. It's the same height depending on whether you're entering this point or leaving it. In addition, I've drawn this pretty obviously so that I can get the figure in. I've drawn this for a ray that's not paraaxial at all. And you have to remember that we're so close down here at the bottom that this line is effectively straight up and down at the interface between these two media. And so, in effect, the arc length here is the arc length from here to here, to a good approximation, is the same as y1 or y2. We can do a little bit of preliminary analysis. The angle of incidence, remember, is the angle the incident beam makes with the normal to the surface, and I've indicated that with beta 1 here. This is theta 1. I've also got our usual angle phi here. That's the angle that the point of the ray is incident at makes when I draw a radius to it. So that's this angle phi. A little bit of analysis shows that if this angle is phi, then these are parallel lines, so this angle here is phi. And then alternating angles, parallel lines, this is also theta 1. So we can, from a little bit of quick geometry, glean that the angle of incidence, beta 1, is equal to theta 1 plus this angle phi. On the other side, we've got a similar kind of story. The emergent ray, the refracted ray, its angle of refraction is beta 2. So there's beta 2. And the angle it makes is theta 1. And again, alternating angles. These are parallel lines here, a transversal. And so if this angle's phi, then that angle's phi. And we see similarly on this side that beta 2 is equal to the sum of theta 2 and phi. So I've got that here as equation 2. So beta 2, theta 2 plus phi. We can apply Snell's law as usual at between the incident ray and the refracted ray. Here I've done that. Let's maybe move that up a little more. So N1 sine beta 1 is equal to N2 sine beta 2. And that being the case, and again, we're looking at paraaxial rays, and so to a good approximation, the sine of the angle is the same as the angle on both sides. The last one is that approximation that this arc length is approximately equal to theta 1, because again, we're right down here in this very small angle paraaxial region. And I know that phi is the arc length, really would be S over R. And to a good approximation, we'll S this arc length is Y1. So I get these four equations. And then it's just a matter of combining them carefully. If I use a 4 in 1 and 2, I can eliminate phi. And that's what I did here. 1 becomes 1 prime, so just substituting y1 over r. And likewise over here, becomes equation 2 becomes 2 prime, theta 2 plus y1 over r. And then at the same time, I changed phi. I simply solved it for beta 2. So beta 2 is n1 over n2 beta 1. And I call these theta 1 prime, theta 2 prime, and equation 1 prime, equation 2 prime, and equation 3 prime. Now then I'll use 1 prime and 2 prime in 3. So just direct substitution for beta 2. That becomes theta 2 plus y1 over r, n1 over n2, and then beta 1 is theta 1 plus y1 over r. And then I solve that for theta 2. Basically take the y1 over r over to the other side and distribute across. I'll write the n1, n2, theta 1 here. And then I've got two values with y1 over r. I've got an n1, n2 times y1 over r. And then I have to subtract 1 over r times y1. So that gives me this minus 1 over r. And then I put that over a common denominator to get this expression. And what you see again is you've got theta 2 in terms of y1 and theta 1. We already have said that depending on which side you're looking at, that y1 and y2 are equal. So y2 is equal to 1 times y1, 0 theta 1. And then I just bring this equation down to here. And then I can write this side in column matrix form. Y2 theta 2 is equal to, just get the matrix of coefficients, 1, 0, minus n2 minus n1 over n2r, and n1 over n2. And simply read off of that what this refraction of the spherical interface, I'm just calling it capital R matrix, and it becomes this. Notice that if I let r go to infinity, this becomes 0, and an interface that has infinite radius is planar. And so this reduces to 1, 0, 0, n1 over n2. And if you go back and look, that was what we got for the refraction at a planar interface. So lots of books don't even introduce that, but it's so easy to get. I usually like to do that as an illustration. Most books will just have this as the refraction of the spherical interface because it also encompasses the case when r goes to infinity.